So good morning. I think I probably know most people that seem to be on the line, but my name's Rick Henry, Senior Lecturer at the University of Auckland and Structural Engineer. And along with my colleague Santiago Pujol from the University of Canterbury, we co-lead the Discipline Theme 2. And so this seminar is around that discipline theme. So I'll bring up our presentation now. Excellent. So we really wanted to provide a bit of an overview of Discipline Theme 2, which is titled Whole of Building Seismic Performance, and really explain a little bit about some of the background of this particular theme and our main sort of research sort of thrusts and sort of projects within that and where we're heading. And so if we put it into context, I think many people would have seen this picture before or might be getting tired of looking at it, but within QuakeCoRE we have our discipline themes and our interdisciplinary programs. And so we sit here in Discipline Theme 2, Whole of Building Performance, and that's, I guess, seen as the sort of structural engineering discipline within QuakeCoRE, and that's sort of the fundamental structural engineering research that we're doing within sort of program that then contributes to a lot of the other areas, particularly within the interdisciplinary programs as well. And so I think there's been an overview of a couple of the discipline themes already, and so this will be sort of similar in terms of just explaining some of the sort of context and main sort of work going on within our theme, and for people to sort of get an idea of that or how that might link in with other activities within QuakeCoRE or projects that may be aligned as well. So when we think about sort of structural engineering, it goes back to sort of how we typically developed our understanding of sort of the behavior of buildings in particular. And really we often think about structures as a lot of different sort of structural systems or components. And if you think about the way that we've developed our design procedures, a lot of it's come from really a more detailed understanding of the component behavior. So when we look at different components, we might have sort of beam, column, frame connections, floor elements, wall elements. And a lot of our sort of past research focuses on understanding the seismic performance or sort of response of these components. And we develop our design rules around those when we're sort of working on design guidelines and standards and things. When we look at buildings, such as the one shown here on the right, you can see that obviously buildings contain a lot of different components and different arrangements, and they're all connected together to form a system. And so when we look at a building, it's perhaps more important to think about how these individual components interact, and particularly the sort of deformation compatibility between them, because they essentially have to act as a single system when the earthquake sort of results in demands on that building, and it's the sort of system response which is going to be crucial to understanding its performance. And so we're sort of moving more in that direction as we conduct our research, and that's sort of driving a lot of what we do in Discipline Theme 2. If we look at some past examples, we can see where this sort of idea of the system response has been really crucial to understanding sort of past earthquake performance in particular. And so a few sort of examples of that which are quite sort of important or obvious in the background to that are the use of precast concrete floors, where people would have heard a lot about this, particularly in recent times, but really comes from the idea that the floor components themselves that we were putting into buildings had really been designed for gravity loads, being that the floor's sort of purpose was to resist gravity, and they, you know, worked okay in that sense and were designed for it. But when we consider their response in an entire system, particularly when they act as a diaphragm for seismic demands, and when they're sort of working together with the seismic system, perhaps a moment resisting frame that surrounds them, the interactions and the deformations that are occurring can cause quite a lot of damage to the floor units themselves. And that's often sort of demands and loads that are well sort of above what we may have considered them to be designed for in the first place. And so that's sort of been one of the reasons why we've seen so much damage to our precast floors in recent earthquakes that we've had, and a lot of effort going into trying to understand that sort of system level, both for the assessment of existing buildings, but also how we design new buildings as well. Another common example is just that really we've seen quite a lot around the repairability and perhaps buildings getting demolished after earthquakes rather than being repaired. And again, it sort of comes back to, in some cases, the fact that although a component or an individual beam or a column or wall may have been able to be repaired from a technical perspective, sometimes the cost of doing that is not sort of economic in terms of the building, particularly when you consider the damage that may have occurred to non-structural components or other aspects in the building, or the damage that you have to actually create to access the structure to repair it. So you're often ripping out ceilings and walls and things just to be able to repair it and then reinstate them. And so thinking about that whole sort of building as a system and everything inside it is really crucial to understanding the performance. And lastly, I guess we're really seeing that perhaps our structures are starting to look a lot more complex. We increasingly sort of have more architectural buildings, which are definitely more appealing, but underneath them, the structural systems are inherently getting a bit more complex. And in particular, we see sort of examples like this of touring a library in Christchurch, which is a fantastic structure, but as a structural system, you've got walls which are post-tension walls forming part of a core structure, combining with another steel frame system, and all of these have to work together in a way that gives you good seismic performance. And so there's a lot that we need to sort of understand around that system and moving to really ensure that we get good performance at the whole building level. So often think about it on this sort of sliding scale for trying to get resilience or repairability into our buildings. We've really got to move from a good understanding of the actual component to the sort of structural system, which is the combination of these components, to the building, which includes both the non-structural components and the contents and everything inside it. And then beyond that, we're thinking about how do buildings interact and communities and sort of cities work when we put them all together. So I think the discipline theme 2 here, talking about whole of building performance, really sits at this third level where we're trying to take some of the understanding we have at the component and system level and really apply that to buildings where we can get a much greater and deeper sort of understanding of how buildings perform and how we can sort of design them in a way that ensures we really get the outcomes we want in terms of resilience or lack of damage and repairability. And as we move further up that scale, that's perhaps some of the challenges that the interdisciplinary programs are addressing as well. And so there's definitely more required in terms of understanding beyond the sort of structural engineering perspective of how these decisions get made as well. So sort of research questions are listed here. I won't go through in a whole lot of detail, but really comes down to sort of really trying to understand and quantify the interactions that occur in buildings when we think about that system response and the damage that may result from that. Sometimes that's damage to sort of expected components in the system due to different demands, but sometimes it's also damage to things that we don't really design for deformations and other sort of components as well. And then looking at sort of solutions and ways in which we can develop buildings and components and things to really mitigate some of that and eliminate sort of negative impacts of those interactions in the building. And lastly, really thinking about the sort of whole of building response, that coming back to sort of understanding the response across a range of hazard levels and limit states and how that affects loss assessments and things as well. So we really integrate that into some of our existing tools and help to make decisions when we get to those more complex sort of processes. So within Discipline Theme 2, it's quite a big community of people. Predominantly this sort of builds on some of the work that was done in Flagship 3 and 4 from the first phase of QuakeCoRE, and really has a pathway into quite a few of the integrated programs, but particularly functional recovery IP1 and residential communities IP2, where some of those direct outcomes of the performance of buildings will be sort of used in a sense of how to sort of bring those together and achieve sort of resilient and good outcomes for the entire community. At last count, I think we had something in the order of about 25 investigators involved, and 3 industry advisors that mostly join our Zoom calls, and about 18 or more students that we already have engaged as sort of aligned projects for the program. So it's really quite a big group of people, perhaps one of the larger of the discipline themes within QuakeCoRE. And so it's kind of been an important sort of role in trying to get that established, to really find a way to sort of glue all of these efforts together that we do in a common sort of framework, which is what we're trying to achieve. We also have really strong international partnerships and collaborations, so we've had really good connections with many people around the world, which have been able to allow us to do things, particularly in QuakeCoRE 1, where we had access to international labs and things. And so QuakeCoRE's really provided an excellent platform for us to leverage that and to achieve some of these things where the scale of the complexity of things gets much more challenging than we might have capability for in New Zealand. So I'll pass over to Santiago, who will go through some of the detail of the theme.
You mind sharing the, or letting me share my screen? I did update one slide.
Cool, let's switch it over then.
So let me try this. Okay, see my screen now?
Yep.
Yeah. So back in April, we had a workshop here at the University of Canterbury where we debated different ideas proposed by the attendees for the theme. And what we did is we had people go to the whiteboard and write down their ideas, and then we had people go around and vote for the ideas. And this list of 8 items that you see here were some of the items that got the most votes. So going from the top, buckling restraint braces, I think that was an issue that was brought up by Greg, and I think of particular interest there might be the issue that braces are usually tested uniaxially, but there might be opportunities here to test things in several directions, because one thing, as Rick is saying, is how the component acts by itself, but another thing is how it interacts with the rest of the structure, and the rest of the structure is going to take the braces out of plane, so to speak, and that's unavoidable. So going down the line, column-based detailing was brought up. As Rick mentioned, the interaction between different lateral load resisting systems and those systems and floors. Diaphragms was brought up, I think, by some practitioners who were indicating that usually diaphragms are much more complex than we imply in our lectures and textbooks, and their design is not necessarily settled, especially when they're irregular, as mentioned in item 5 there. Of course, one of the main issues here to keep buildings functional, to make sure that the building works as a whole, is that, as item 6 suggests, the non-structural elements and the structural elements need to work well together. That, by the way, may imply that we design buildings for lower drift limits. At least that's an option, as implied by item 7. And during the workshop, examples of successful use of lower drift limits were mentioned, and I'll allude to them again in a couple of slides. And then last, of course, to support all of these ideas, we need to run simulations, numerical, and we hope maybe some physical simulations, shake table tests, if you will, to make sure that what we propose works. So based on this, there are, in this theme, there are 4 thrusts we're calling. And The hope is that in the RFP that came out recently and the call for applications for scholarships, we'll be able to find opportunities to address some of these ideas through these thrusts. The first one that I list here is implication of design decisions. Again, that would refer to, say, reducing drift limits or making other adjustments to the design standards so that we don't, say, repeat the experience of Christchurch where so many buildings had to be demolished after the earthquake. Second thrust here within the theme is the mentioned interaction between different structural components. That's of course related to item 4 here, the interactions between non-structural components and the structure. And then in between there, item 3 is once again about diaphragms and how do we make sure they work better and we avoid issues like what we had in, say, QuakeCoRE. About thrust 1, the implication of design methods or changes to design methods. As I keep mentioning, one of the opportunities here is to maybe consider the idea of reducing drift limits. And that's been mentioned repeatedly, at least since I moved to New Zealand about a year and a half ago. And I think a number of people have been saying this. For example, Didier Pettinga comes to mind right away. I think Stu in the workshop also brought this up and mentioned that designers are already using lower drift limits. And I put a picture here of a building in Viña del Mar that I like very much. It's called Torres del Sol, and it's survived 2 big earthquakes. And I like the building because it has robust, abundant shear walls. But when you look at it from the outside, you cannot tell. You don't see any structure. You see window everywhere. But inside, there's lots of wall. It's a very robust building designed to meet the very stringent drift limits they have in Chile. So there are opportunities to make livable, if you will, useful, beautiful, perhaps, buildings. We don't need to build boxes, bunkers, to adjust things like the drift limit. But that's just an option. There might be other opportunities. In regards to lowering the drift limit, one sort of tricky aspect there is that if the alternative then is to design what we call here in New Zealand nominally ductile or limited ductility structures, that might backfire if that comes at the expense of reducing the detailing or decreasing the quality of the detailing. That we might need to think about that. To reduce the drift limit doesn't necessarily mean we need to relax the detailing, because the detailing is sort of the suspenders that go along with the belt to make sure things work, even when we have to face the unexpected, like it happened here in Christchurch when the earthquake was much bigger than was expected. That's bound to happen again. We have to admit that. I think what is being done in terms of estimating future ground motion in New Zealand is fantastic and commendable. But we have to admit we might be wrong. And for that, we need the detailing in addition to maybe stricter design limits. Then in item C, idea there is that we need to make sure that whatever is done works not only for the, say, ultimate limit state, but it should be checked for the other limit states too. And all of that needs to be done in the context that we don't only need to think of the new buildings, we need to also think of the existing buildings or the buildings after earthquakes, and how do we assess them to make sure we fix the ones that really need to be fixed, and we keep using the ones that can be used again without having to demolish them unnecessarily. So that's the thrust 1. how do we tweak the design standards so things work well? So the building works well as an entity, as a whole. Thrust 2, again, is about the interaction between the different structural components. And here we can mention the interaction between the lateral load resisting system and the floors, like Rick has mentioned. Then the interaction between the different lateral load resisting systems themselves, and the interaction between connected buildings. And by the way, something that was brought up, and it's related to this, something that was brought up in the workshop is that very commonly we're told now designers are using mixed systems or hybrid, if you will, systems where maybe the gravity system is steel and then there's a concrete wall that provides lateral stiffness. That interaction requires careful study, and I know there's already a project looking at connections between steel components and shear walls. That's critical because that connection has to work. Even if the shear wall is designed well, even if the the gravity system works well, that connection is critical. That kind of thing is what we're referring to in Thrust 2. For Thrust 3, again, the focus is on the diaphragms, and the items of interest here are the precast floor diaphragms in existing buildings. We all know how important that is for New Zealand, and I think Des and Ken and Tim have done have made a lot of progress with this. I'm sure that's going to have great benefit, but there may be more issues that come up. The interaction between all these sort of independent components, it's complex, especially if you have irregular floor diaphragms like the one illustrated there on the right, which is a building that has been projected to be built in Bogota, Colombia. And then last but not least, we have the idea of maybe using different floor systems. I find here in New Zealand, the flat slab that is very popular in California, it's almost not used, or I don't see it often. Maybe that deserves some consideration, or why not maybe using different materials to make the floors that are so heavy in our buildings, like timber. I understand the Japanese are quite interested in that idea, again, because the building will weigh less and because they have a lot of timber, apparently, in Japan. And then in Thrust 4, again, we have the very important issue of the non-structural elements, or like Greg says, the non-skeletal elements. And there are, of course, all sorts of issues to investigate there. I happen to know, for instance, there are firms right now struggling to decide what's the deformation tolerance, if you will, of cladding panels that were built maybe a couple of decades ago without clear consideration for their deformability. It's not easy. We don't quite have the methods to decide how much you can deform a structure before conventional attachments to the cladding pop, so to speak. One important issue that has been highlighted there as item A is that I'm not sure that the line drawn between what's affected by acceleration and what's affected by deformation has been drawn clearly. We keep being told repeatedly, oh yeah, ceilings and sprinklers are affected by acceleration, not deformation. And therefore, it seems when people go and classify after an earthquake, they classify damage. Anything that is affecting the sprinklers is classified as damage caused by acceleration, and that by implication immediately says that stiffer buildings are no good. Yet you have the Chilean experience that says the opposite. So there's a little bit of a contradiction there. I think many of you are probably familiar with the case of the Olive View Hospital in California that was destroyed by the San Fernando earthquake. And then it was rebuilt with not just concrete shear walls, but steel shear walls. They went to the opposite end of the spectrum. And I was always told that experience was sour because a lot of non-structural elements were damaged. I came along a paper by Chelebi the other day, who described what happened to the building, and he says in that paper that the building had to be the functioning of the building had to be interrupted, but he said the interruption was rather short. And I don't remember what he meant specifically by that, but those are the words that I quoted in some other paper. And he said the interruption was caused by damage to sprinklers. But get this, the damage to sprinklers happened in the first story, not the top story where the acceleration was 2g, but in the first one where the acceleration was at least 3 times smaller. Very interesting. You know, it begs the question whether we've been looking at the issue of, say, in this case, the sprinklers correctly. Are they sensitive only to acceleration, or maybe they are sensitive to a combination of acceleration and deformation imposed by the deformations of their support? And of course, there's always the question that anyone should ask: do we need to find a solution to the sprinklers and the ceilings in the structure? Do we need to fix their performance by changing the structure, or can we fix their performance by changing their attachments to the structure? Right? That I'm not sure has been addressed well, but I know there are people on the call here who know much more about non-structural elements than I do. It's not my area. All right, and then last, there's the interaction between the different non-structural elements. That is quite important too. We want to stress in this theme that we need to not only look at our simulations. No, we need to not only think, we need to look too. It's very easy to choose one or the other. We need to do both. We need to look at what has happened, what has been done elsewhere, and we need to run our numbers too, and we need to do our thinking too, but we need to do both. So we want to make sure that in this theme and these thrusts, we look at the data from previous earthquakes, and we have lots of it. We have data from Kumamoto, we have earthquake data from Taiwan, we have data from Chile, and in many cases we have drawings and records. The other day I came across the full record from the Christchurch earthquakes with drawings were building after building after building. It's important we look at those. It's important that whatever we say should be done is consistent what has actually happened, not just consistent with some numbers that we run on the computer. And we have data also from shake table tests, like the one shown here on the right, 10-story full-scale shake table test done in Japan, and more. We just signed a memorandum of understanding with BRI, where they're saying they're happy to share their test data, which is rich. So with that, I think I pass it back to you, Rick. Thank you.
Cool. I'll just use your slides and keep going. So yeah.
Sure. Yeah.
Yeah, so I think that gives a really good overview of sort of the main sort of thrust areas that we're focusing on, and that it is something that aligns a lot of projects that are ongoing. So we have quite a few students that are midway through PhDs and doing projects that are aligned to the theme, as well as new projects that we're funding from the program as well. So it's been an exercise in sort of trying to understand the landscape of that, and really the intent of the whole of building sort of focus is to be able to bring some of that together and work on something that leads to a common goal. So we've done quite a bit around sort of mapping some of those projects and having regular meetings recently to sort of go through some of those existing aligned projects to sort of focus it. So if it jump to the next slide. So one sort of thing around that focus is sort of looking at the different simulations we do. And so just in the last meeting, we had a number of different presentations showing the use of different models and simulation sort of frameworks to address problems. And we've got some really quite powerful tools in that area, and there's good sort of potential to leverage that by aligning some of the goals of different projects. So, perhaps Regan's been developing models to do studies on long duration earthquake, and he's been looking at the moment resisting frame. Maybe we want to take some of the wall models that we've developed from another project and sort of substitute them in to get a comparison. So being able to do some more comparative studies around case study buildings or common typologies will allow us to really cut across some of the different structural systems and break down some of the silos of us sort of each working in our own individual sort of preferred material or system. And so that's one area where we want to sort of bring together some of the different activities in QuakeCoRE. And then the next area is in large scale tests. And so I think we jump to the next slide, Santiago. So most will be aware that in sort of first phase of QuakeCoRE, we had really some quite successful projects that leveraged international collaborations where we were able to access testing facilities. And so a few of those are shown here, where we had 7-story test in Taiwan led by Ken and Tomomi, which has been a really great sort of collaboration that's strengthened some of our ties with their research centre Incre. We also had test up at Tongji University out of the Eiley Research Centre, where we did a 2-story concrete building, and coming up we have the robust building being tested there as well. And then some really strong collaboration, as Santiago was mentioning, with Japanese researchers, and a lot of the tests that they've done, they're very open to sharing that data and allowing us to participate in those to sort of access that as well, and really beneficial to do that. And so what we're thinking in particular in DT2 is that there's a lot of efforts where if we combine those objectives together, perhaps the end goal could be another one of these large scale tests. And so that might include sort of taking some of those concepts of lower drift demands. Maybe we come up with a building design where we can test some different structural systems to compare the drift limits and the implication of that across sort of a standardized building. We can include some of these non-structural components and vary some of those as well. So really bringing together those objectives, perhaps that's a really good target to align different projects and again be able to leverage some of these international collaborations to come up with another great outcome from that. And so last sort of part is how to get involved. So many people within the DT2 team have sort of been joining regular Zoom calls already. We've had quite a few monthly meetings at a slightly less than monthly schedule recently to try and come through some of those thrust areas to understand what's happening. And so we've built up our wiki page as well, and you can jump on that to have a bit of an overview of the project, links to the meetings and invites for that, as well as the past meetings with slides and things that we have as well. So all of that content's sort of been put on the wiki for people to access and share some of that information, the workshop notes as well, and some of those large scale tests. So we'll keep populating that as we go, but really open to sort of understanding how this connects in with other parts of QuakeCoRE as well. So particularly looking at sort of establishing good sort of connections between common sort of parts of our discipline themes and into those integrated programs too. So as we build the research up and some of the projects around that, then we'll be looking more at how that sort of brings together. So I think that's all we wanted to cover, and thanks very much. I think we've got time for some questions if people have any questions they want to ask.
Rick, may I add something relative to that large-scale test possibility at this point?
Yeah.
And that is that the sooner we start thinking about it, the better. And if there might be chances to think sort of outside the box, to use a cliche, to set up a test system, not too different from what has been done very cleverly at Robust, to use a setup to test different ideas. for example, and this is just a random idea, it is not necessarily the best, but one could, for instance, set up a rather flexible, maybe steel frame, and then a shear wall, and test them connected first, and see how they interact and so on, and then see how they say non-structural elements respond to that condition, and then maybe separate them and test them again and ask the same questions. But again, that's just a random idea, and I'm sure there will be better ones, but it would pay off to start thinking about it now. Even if we don't get to do the test eventually, it might inform our even simulations, for instance.
Agreed.
I see several microphones coming up live, so.
This is Greg. Thank you, Rick and Santiago, for putting this together. And it's a huge amount of work just to try and assimilate everything. And I think what you're doing here is saying, where is earthquake engineering going in this sort of structural space, and not in terms of just some sort of new device or new finite element method, but in terms of really solving a real problem of an actual structure, so that we can end up with better structures and better assessments and better repairability and all that sort of stuff. So I just want to say thank you to that for that first. And my comment, this is just a short comment regarding Santiago's idea, is that we did some testing on the University of Auckland shaking table a few years ago, looking at how to re-straighten a building after an earthquake. So if it's gone over in one way, what do you do, and how you could use aftershocks and things to do that. And we didn't do that. It was a really fun project. The student, when he first arrived, said, "There's no literature on that." I said, "Isn't that good?" And he made a big contribution there. But he was able to use a frame with friction devices, and he would be able to get the frame to put it in a shake. He'd find a record which would get it to go over a fair way, and then he'd use other devices and things, and then shake it again and see what happened. And some devices made it actually go further in the other direction. It wasn't what we wanted, and the devices were too effective. It certainly, so he ran I don't know, hundreds of earthquakes with this. Really reliable performance, being able to get it over in one direction. So it would be possible to do that as using something like a frame like that. Eventually, the fatigue life of everything, was reached, and it wasn't good for much. But it went through a lot first. But it could be done with different sorts of NSE or non-skeletal or non-structural elements, and different sorts of flooring system and flooring connections and other things. On the robust project, we've just got a very limited time frame, and I'm sure when it comes down to it, we'll have exactly the same thing with anything we do, but just because of time constraints and cost constraints, lab constraints. But it helps us think about what is important and what we can do with it. So support.
That reminds me, I think I asked you before, but I forget what you told me. I'm sorry. Do you have non-structural elements in the robust project that
okay, what we
can
have
study the performance of? Yeah.
Yes. So the robust project, one of the things that was really in order to get it going, the friction connections, the range of friction connections, was something which was really, really new to the Chinese, and they were wanting to understand that. But in order to get the sponsorship from the New Zealand side, the way we got that from many of the sponsors was because of the emphasis on again, I call it non-skeletal element, because many of these non-structural elements actually have a structural contribution. So it's a total misnomer to call them non-structural elements when they contribute to the structural response. And so if they're not part of the skeleton, they're not part of the beams, columns, diaphragm. And some of these non-skeletal elements we're trying to make non-structural so that they don't contribute to the response very much. But they still, all of them contribute some way, even if they're rocking, they want to rock back, and that provides some sort of recentering tendency for the structure. So probably they all have some sort of structural impact, even if it's just a mass one. But yes, it's the last test, and we've got every element you can imagine, all the common ones: glazed curtain walls, precast concrete panels, internal partition walls. We've got ceilings, we've got piping, and we've got contents. And
sprinklers,
the piping for the sprinklers. Yeah. I don't know if the actual sprinkler head is on there, but it's and I'd have to check with Rajesh about that. But
yeah, it is there, Greg.
Oh, thank you.
Yeah.
There's a lot of feedback, but Greg, so I wonder, because I know you're going to use different types of bracing systems in the different series of tests. Is there an opportunity there to test, to what extent acceleration harms more than displacement, or vice versa? Because I imagine the different bracing systems will produce different levels of drift and different levels of acceleration for the same non-structural elements.
Yeah, there's certainly opportunity. However, when we go to the lab, we're always told, cut it back, cut it back, cut it back. And so in the end, what we've done is we've only got one major test series. We've actually got 9 different structures. And we've only got one structure where we have all the non-skeletal elements placed on them. And we've decided to put that one on the structure which will have the biggest drift demand. The limitations to stop us from doing the other ones time and cost, and other people wanting to get into the Tongji lab. It's really easy to do. We could do it very, very easily. However, we're told chop it back, and so we're at the stage we are now because of all these people saying every time we chop it back, we give it to people for comment, and they say chop it back more, and so yes, it would be really easy to do, but the logistics it's and I'm sure we'll have the same thing when we have our test setups in New Zealand universities or elsewhere for other places.
Thank you.
Cool. Any other questions from anyone?
I thought I saw Paul's microphone alive.
No. Well, I think if that's it, then we'll call it a day for that. And I think just a reminder that this is sort of part of the regular seminar series, and so I think that the next one is scheduled for the 29th of October, and that's going to be Elan and John Hopkins focusing on the discipline theme 3, which is law, planning, and economics. So I think that'll be the next one up. If you want to tune in, and I'm sure there'll be an email reminder of that as it gets a bit closer to the time. So thanks for joining. Hope that was useful for people, and feel free to contact Santiago or myself if you've got any questions or want to discuss further. Cheers.
Thank you, Rick.